Must be recording. Great. Okay. Okay, so hello, and sorry this took so long. Had a few technical difficulties this week. We will try to not make that a habit. I've never had my battery give out, so that's something that I am now aware of. Okay, so what I've got for you today is the GIL tutorial that also Professor Peluso has up. So if you've already watched that, this is probably you don't probably need to watch all of this. I will do the data tree controls in a different fashion than Peluso. So he introduces you to a little more complex level of path mapper, and we're going to keep things relatively simple by using things such as flatten and list item and call index and and also our right click controls, right? We have the right click where we can just choose graft or flatten or simplify, um, and that's how we're going to keep it familiar for this. Okay, so but always remember that you have this web page that Peluso has for all of his classes, but for ours in particular, we have ARC 207, DC3 Fall 2020, and you can go in here and you can look at the syllabus and you can check out all of our tutorials that we've already walked through. These are all Peluso's videos that he's had up on YouTube. And he has more, of course. So if you go to his channel and follow him, you can learn, a ton more. But if you want to check out the ones for our class, these are always available. So for instance, this week we have the assignment here as being very specifically set to shark gills, right? So we're using this case study by Amanda Levette, where she's detailed this sort of curvature in her facade of her building. Okay, so what you can do is you can take what we'll learn today in class and apply it to you can do it vertically or as a roof or maybe as another more wild warping structure. But I'd be curious to see how you apply the parametric nature of this week. Okay, so 3 different parametric iterations, and then you can follow the script that we do today. It should be relatively simple, I would think, given that we're going to walk through it together, and there's also this other tutorial out there for you. Then the other thing that we're going to talk about in the second half of class today is that we're going to introduce you to Lunchbox. So if you didn't already do this, you're going to want to download Lunchbox for Grasshopper, and this is going to be useful for you, I think, in the future because it has certain structures and divisions already built into it, making it much easier for you to control your surfaces and space frames. For instance, this already has a space frame capsule in it, so you don't have to go through all the wicked steps that I taught you. You can just pull down a capsule and it's already there for you. So I was the mean one. So download Lunchbox and get that installed on your computer. You should be able to go to your Grasshopper interface and go to Special Folders under File. You have Special Folders. Go to the Components folder, and in here you'll see you should see these Grasshopper assemblies of what you have installed. Okay. So if you don't see it there, you should be able to drag and drop it I thought I remembered that Lunchbox was an install like another program, but maybe I'm wrong. So you'll have to play with it and see. If you have any issues, you can give me a message and I can try to help. Otherwise, Google's your best friend. Um, I'm sure if you have the problem, somebody else has also had the problem. So once it is installed, you should see this update here in your tabs, right? So if you go here, you should be able to click on that, and you can see these new capsules that are available to you. And like I said, Lunchbox is great for it has these default shapes or default surfaces. Well, not default, but they're pre-made for you. So if you wanted a Mobius surface or the hyperbolic paraboloid, these things that are complex curvature. It's complex curvature made easy. Okay, so you don't have to go through the steps of trying to figure out how to make it. It already has a helicoid surface for you. Um, so that's one thing. The other thing is what we're going to talk about today is how to use this kind of division or paneling of your surface. Okay, so these are the easy buttons for everything that we've done before. So there's panels and then there's structure. Structure is going to be a point and curve grid for you for you to pipe or uh, use it to whatever advantage you want. And then you have your utilities. This is where we're going to actually start from today. We're going to use rebuild surface. That's in the very first part of our script. So like I said, you will need Lunchbox in order to perform this division. Okay. So, and then workflow, of course, is it's an Excel reader and writer, and it can talk in between your Excel file where you can have a series of data and Grasshopper. So this is really great if you have a long list of commands or data or XY coordinates or whatever. You can then you can start to talk between programs. So if you ever start working for, I don't know, a structural engineer or something, you might need to write between a a structured structural Excel file and Grasshopper, and this would allow you to do that. Okay, but for today, let's turn this on. Preview. Okay, so for today we're going to be walking through the gills. Okay, so that's the first part of class. That's here. This is what we're going to walk through. Looks relatively simple and harmless. I think most of the stuff you already know. We're just going to be putting it together. Then the second part of class is a little bit of Lunchbox. Okay, so I'm not going to preview on because it's quite a bit of division and panelization. And then the last thing we're going to do is I'm going to turn this on. It might take a second because it's a little bit complex for the geometry to update to. But what this is doing is it's reading the curvature of it's reading my curvature and it's applying a very simple circle. And it's adjusting the scale of that circle based on the curvature. Okay, so these are kind of like my freckles for my gills. Okay, so that'll be the second part of the class. So, and notice I'm having some difficulties with my Grasshopper updating. It's wanting to be very slow, and sometimes it just disappears. And I've had that happen many a times, and quite often it's just a matter of retyping in Grasshopper, and it will the window, which should be minimized. Okay, it should be minimized like this if you're not working in it, right? It sometimes will just go away. So just retype in the command, and it should open up again. Okay, so I'm going to preview this off so that we're not wasting all of our memory and graphics and stuff. And then I'm going to start on the gills. Okay, so the first part of this should be relatively simple and the same as what Pelusa does in this video. So if you've already done that, like I said, this will be redundant. The second part is the deformed surface, and this is where we're going to pull up that surface to achieve the curvature is a base surface, right? So if I turn my gills off, you can see the base surface. That's the second part of the script where we get our what we're going to divide in the next step. Okay, and here I think is a key difference of how we perform the same function, which is we end up picking picking a row of these points to move up in Z space. Okay, that's the goal, is to move them up in Z space to get this curvature and to form those points. Okay, um, so if you've already watched the other video, then you can skip forward to that point. But if you haven't, then let's walk through how we get to this curve. Okay. Forgive the sirens. I don't know why today is crazy, but things have just been, there have been so many sirens. Oh yeah, yeah, I just hope people are okay. Okay, so I'm going to turn off my grid, and then I'm going to, do I want to see yeah, I don't want to see the grid, so we're just going to, well, I do want to see, oh, there we go. So, show grid, no, okay. I do want to see the axis though, so I know where 0, 0 is. Okay, so let's get started. So our first step is to create a plane. We need a plane here that's going to act as our base surface. So we can do that by just typing in plane surface. Okay, here we go, plane surface. And it's going to find itself at the 0, 0, x, y coordinate, right? That's the center point, and then it's going to have a default of x set to 10 and negative 10. And then y is also going to be 10 and negative 10. So what we want to do is we want to control the x and the y length. So I'm going to give it a default of, say, 100. And now my units are in feet. So I just keep that in mind if you're in inches or feet or millimeters or whatever you're in. But mine are in feet. So this is 100 feet now in the y direction, and this is 100 feet now in the x direction, with my plane staying at 0, 0, x, y. If I want to reorient this, I can give it another axis to orient to. So I have a YZ plane, then I can flip that and reorient my work surface so that it is in the Z direction. I don't want to do that, but it is an option. Okay, so if you wanted that facade that Amanda Levette has, that is a way of achieving that. Okay, but right now this is going to be, I think this is going to act more like a roof, so we're going to keep it horizontal. Okay, so I'm going to turn off my lunchbox there. Okay, so I have my planar surface. So what I need to do is actually I want to rebuild this so I have a number of points. Like we saw, we had a number of points in a sort of grid fashion. I want to find those. So in order to do that, I need that. Oh, I actually wanted my lunchbox. So I wanted my rebuild surface, which is under the lunchbox tab of utilities. Okay. So rebuild surface is under utilities. So what that does for me, if I put my plane into my surface, is it will adjust the point control grid that makes up the surface to a new U and V number. Okay, and we'll see that if we do I think it's how's it, surface points, right? Surface points. There we go. So what this acts like, see, I think of points on in Rhino space. It's the same command. Okay, so if I go into my Rhino space and I choose a rectangular surface, I hold shift here, and I create a new surface, I type in points on, it will give me the control points of that surface, right? We learned this the other week. Okay, but if I want to have the same effect as this, right? So what we're doing here is we're rebuilding the surface and we're giving it a new grid of control points. I can do the same thing in Rhino space where I select this surface that I've made in Rhino, type in rebuild, and then give it a new point count, okay? And if I turn in points on, I will get a similar effect, right? These are my control points, and as I select them, not the surface, I can move these to control the curvature and the form of that original, very simple surface. Okay, it was just a 2-point rectangle to start. So, so back to Grasshopper. So what we're doing here is we're essentially doing the exact same thing, but just in Grasshopper space. Okay, so I have my points on, I have my surface points, great. I'm going to want to control the U and the V divisions. So I'm going to bring down a number slider and input that into both the U and the V. And then I can adjust that to somewhere around 7 or 8. But this will actually be important later because we will reuse that number. Okay, so these are all together. I think I'm fairly happy with this. I think the other thing that we do is we take a look at the point list just to kind of have an idea of where the origin is and what direction that point list is going. So if I give it a point list and up that size, I can kind of see where my origin is, right? We knew it was at 0, 0, but now we know the direction is going to go in the V direction, or Y, right? So U is X and V is Y. So it's working in the V axis. Okay, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are my lists of points, and I'm going to need to control them as such. Okay, so that's kind of a hint for the next step. All right, so that's the first part of our script. I'm going to give it a scribble. Okay, and we're going to call this, I guess, a rebuild surface, or maybe surface division, whatever is easier for you to remember. I do wonder if you can hear the motorcycles that rev up next to my place. Not that I mind, but it is kind of distracting for you. Okay, so there we go. We have our point grid. Now we want to extract one of these rows, and we want to raise it in the Z direction. Okay, so we need to, in order to do this, we have to think about how we get those points. Okay, so how do I get a list of these points in this direction from this capsule? Okay, so panel helps. What does the panel say? Okay, it's like our crystal ball, it makes everything clear. Okay, so let's take a look. So we have one solid list of, we hover over this, 49 points. Okay, so I must have divided by 7. Yes, okay. So let's do 8. So we have 64. Okay, so I have 64 points. They're all in one list. So in order to really extract a part of this list, right? We just want a part of it. We want these points in this direction. In order to get them, I really want to partition. I want to just take a chunk of this list. And we can do that if we do partition list, okay? Partition list. Because that is going to separate these. And from one solid list of 64 points, it will give us 8 lists of 8 points. So That's if we change the size, right? So if we remember partition list, we used this before, where we have the list, and then it will give us chunks, um, where its default is size is set to 3 and 2. Okay, so it has 3 values in this first list, 2 values, 3 values, 2 values. Okay, so that's what partition list is doing for us, but we want that 8 lists of 8 items, right? So we need to control the size to be 8 items in one list, and then there should be 8 of those lists. Okay, so I'm going to go back over here and use this number that is our rebuild surface as our partition list size. Okay, so that should correct this. So now we have 8 values, and there should be 1, 2, 3, 4, 5, 6, 7, 8, right? Remember, because we start at 0, so the last number should be 7, but there are a total of 8 lists. Okay, so we have our chunks, we have our list, looking good. Now if I do a branch, so I have a tree branch, and if I take this and input, it's going to say no data. Well, it's because we don't have a path for it just yet. But what we're doing is we're going to take, let's copy and paste so we see both these. Okay. What we're going to do with this tree branch is we're going to take really just one of these lists. Okay, that's what this is doing for us. So it's going to select one branch of data and leave all the rest. They're not going to matter. Okay, and remember these are each groupings of points. So 0, 1, 2, 3, 4, 5, 6, 7, this first branch is actually these points, 0, 1, 2, 3, 4, 5, 6, 7. And this next branch is, or this next line of points, okay, 8, 9, to 15, and so forth. So in thinking about this, if I want to just select one of these, which is now a branch of points, I need to give it a path, which is probably somewhere around the middle, right? So that's these guys. I have my paths, my 0, my 1, my 2, my 3, okay? So that's going to probably be like a 3 or a 4 for my path, okay? And notice it doesn't like that. And that is because it has too many subdivisions. So it has too many sub branches. Okay, so my first number here is 0 for each one of these. Okay, that's technically all a part of the same tree, the same trunk. So this needs a clear delineation of which branch we want. Okay, because this is one solid branch of zeros, and then there's another solid branch of the same list of zeros, and then we have that it finally splitting off into new branches of information. So if we have the same stream, it's actually trying to divide. It's trying to take that path from much earlier on in the branching, and it doesn't have that as an option, right? Because they're all 0, so they're all matching. So if I simplify, if I right click on this and I simplify, that's going to simplify my branch structure so that all of those similar streams of data all branch at the same time now. They'll branch at 1 at the first step. Okay, so it's like it's a bit like we're just culling all of the other branches and only finding the one that is the most important. Okay, so it simplifies it now into one stream where it's all being divided into 8 different paths. And now, because we have 8 different simple paths, it can give us a feedback, right? So it can output one of those paths for us, which is this guy. Okay, So I've had this selected, and you can see that it's selected now the fourth path. So if we count this 1, 0, 1, 2, 3, 4, that's correct, right? And it is starting from 0, and it's working its way up these numbers. So as I move this, I can see that these things update. Okay, so that looks correct, but the issue is that we actually want to select the row in this direction, right? So that's what our previous, oh, let's look at this guy. That's what our hill is, right? So we need to move a line of this data along that same axis. So to do that, all we really need to do is use what is called a flip matrix. And we've done that before, if you remember, where we had a stream of data and it's oriented in one direction, and what it does is it flips it and it reorients it in the perpendicular direction for us. Okay. So now I've just input my chunks with that same simplified data, right? The same simplified branch structure. And now that path is flipped so that all of my zeros are making up a new list, and all my ones are making up a second list, and all my twos are making up a third list, and so on. So if I'm selecting 3 here, all of these all of the 3s in this list should align to the list of points in my new branch. Okay, so if I select this, you can see here that point 3, which is here, should be 0, 40, 0, 0, 40, 0, and point 11 should be the next item in the second branch of my chunks, right? It should be here. 6.66, blah, 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 40, 0. And if I look here, it says 6.666, 40, 0. So it's what flip matrix has done is it's just, it is reoriented my list structure so that all my zeros are grouped together in a new list, and all my ones are grouped together, and my twos are grouped together, and so forth. Okay, so that's how controlling your knowing how your data trees are working and will help you manage them. Okay, so so now we have one of our rows, our middle rows selected. Okay, we'll leave it at 3 or 4, and now we need to move that in the z-axis and deform our points. So deform this curve to get the curvature that we need. Okay, so I'm going to move these over so it's a little less distracting. Shift these 2 down so you can still see them. And then what we need to do is we actually need to find this, so we did the branch, right? Now we need to do point deform. And what that's going to do is it's going to deform our original plane using the location of our new moved points, okay? So we need point deform. Okay, point deform here. And we have 3 inputs. Our first input is the geometry to deform, which is going to be not this, it's actually going to be our surface, right? So it has to go all the way back. We have to go to our rebuild surface. So that rebuilt surface that we did is our geometry input. That's what we want to deform. And then the points are going to be this branch that we've chosen, okay? And that's going to be in the z-axis, right? We want to move these in the z-axis. So we're going to give that a z motion. And notice it doesn't like us again. Okay, if we click on our bubble, which these are helpful, it says you must apply equal number of points and motion vectors. So if we look at our motion vector here, we'll see that it has just one of these. So we need this to actually be, well, this needs to match the same number as in our list back here, right? These need to be 8 list items long. So what we're going to do is we can give this well, we can't give it a factor, right? Because the factor is going to tell how high the z moves, but we can give it a repeat data, which is a new capsule for me as well, in that I very rarely had ever thought to use it. But what that does is it takes your data and it kind of just copies, and it copies it a certain number of times in one list for you. Okay, so notice it doesn't have any input for its length, but if we put that number slider for our rebuild surface, right, that original 8, if I input that for the length, it will then give it, it will just create 8 line items of the exact same value for whatever we put in for our z factor. So notice the default is of course 1 foot, which we don't want, but we can give it more, much more. So like say 50. 50 would be good since this is 100 feet in each direction. 50 seems about appropriate, about half the distance. Okay, so I'm going to input that now into my motion vector, and now we get a little bit, we get a hill. We get something that looks more like what we want. Okay, so all right, so that's good. We can group these together and we can organize things so that they're not so haphazard. Though I don't know, I think I've gotten worse at organizing as I've gotten more, just a little more careless with how I approach it. Maybe it's confidence, or maybe I'm just turning lazy as I get older. But I'm going to group these and bring them out so that they are separate items, and I'm going to call this first one, right? This is where our location is of our curve, of our wave. We'll call it a wave. Say wave. Ooh. Wave location. Okay. And this one's going to be the wave height, right? So our 50 was our wave height. So we can make that high and low and whatever we want to do. Okay. So I think that's good. I'll give this a scribble, and that's the part 2 of our GIL script. So it's a little different. I'll say a base, a deformed surface. It's a little different from the tutorial on the class page, but I think that you can use PathMapper or other avenues of extracting that list, but I think tree branch is a good capsule to know if you want to take a list out of a series of lists, right? So this is a new helpful capsule for you, as is repeat data. But I think that's in the video. That is in the video. That's where I got it from. Yeah. So that's a good capsule to know. And then partition lists, of course, we've done before, but knowing that these lists have to talk to each other, and that we can't just if I unsimplify this, everything turns red, right? And that's because there's too many branches. There's too many sub branches happening. So if I simplify that and I make it one simple path, our tree branch knows how to work, right? It knows which path to choose, and our repeat data also knows how to talk when it has how to translate our z vector from one list item to 8. Okay, so simple concepts, but they're very useful when you start to troubleshoot your script. So as you're working through things, nothing's ever clear. For Grasshopper, nothing is super easy. You're going to have to put in some effort to figure it out, and that's true for, I think, however advanced you get. It's just a matter of stubbornness and memory, right? Knowing these tricks and knowing kind of what to look out for in your list control, it will really help. Okay, um, so the next part of this then is we need to, and I'm going to turn this off, the first part, since he's kind of distracting now. Okay, so the next part of this is that we need to divide this surface so that we get a series of base curves, um, from which to loft from, and we're lofting from the base surface divisions onto a raised curve from this. Okay, so that's not very descriptive from what we're looking at. So let's walk through it. Okay, so first thing we need to do is we need to get some points on here so that we have um, something to talk about. Okay, so let's divide a surface. Okay, I'm going to divide surface. I put my deformed surface, right? My deformed surface, and I put that into the divide surface, and I get a default of u of 10 points and 10 points. Okay, at least that's what I think. But if I count these, I have 0, 1, 2, 3. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I actually have 11 points from my surface divide. And that is because what this is doing is actually dividing it into strips, right? So this strip is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But to complete the 10 count is 11 points. So something to note as we work through the Gaussian, the graph mapper that we learned last week. Okay, and we have to give it a range and stuff. So we have to remember that when we divide the surface, we actually get 11 points as an output. Okay, if we have if we put in 10 for our u and v. So that means if we put in 8 for our u and v, our output will be 9, and so forth. Okay, so I'm going to just give it, I'm going to give this a 5, 4 or something. And then I'm going to give this a higher count of, so we can tell the difference, okay? There should be a stark contrast between our V count, right? Our V count should have more, and then our U count will have less, okay? And actually this guy is going to act as our gill maker, our gill divisions. So this is going to be the number of gills in our our script. Okay, so we might want to pull him out as something special. And then this guy is going to be what we want this to be a little bit higher because this is what we're going to use as the input for our movement to create our remapped curve using the graph mapper. So we kind of want more points there to make that a smoother curvature. Okay. So we have those. Now we need to think about moving these, okay? So we want to use the same thing that we did last week, which was the graph mapper, okay? So we know that we're going to use that as our means of remapping these in the z direction. We know that we want to move these, so we're going to need to move capsule, okay? For moving in the z direction, we're going to need to move them. And then we're going to need a z motion. Okay, z motion. And we're going to need to input our graph mapper. Notice everything goes orange. Okay, well that's because we don't have any information for this. So if we remember before, we had to, our rules for using graph mappers, it needed two things in order to really work. It needed a construct domain. Okay, construct domain here, the 0 to 1. And then it also needed a range, a number of steps to work from. So our construct domain can go into our range, and our range into our graph mapper. Okay, now it's somewhat happier. But now we need to control those numbers and the graph, right? We need to give it a certain a series of numbers for which each of these points needs to move up in space. Okay, and so this is going to give us our increments. If we right-click on our graph mapper and we choose graph type and go to Gaussian, now we get something that looks a little more familiar, right? This is going to control that curvature. And then if we think about the number of steps here, the steps are going to need to match the number of points that we have on those curves. Okay, so because each of these is going to need its own z vector, right? It's similar from what we just talked about, that in this example for our repeat data, this gave us a z vector and it gave us 7 more on top of the original z vector, right? So it did unit times 8, and then we got 8 vectors to align with our list of 8. But for here, we need a similar thing where our z vector is being input, and he has actually 11 localized values, but that's going to be for, that's based on the default, I think here, which is already set to 10. Okay, so that's probably fine, but we are going to input our v count just so that stays the same. Okay, so if I do decide to move this up and down, then our number of z vectors will align with that number. Now, this brings us to what we talked about last week, was that if we input the range for last week, the warping tower, right, and we had to input this so that it was x minus 1, and that was so that our range output aligned with our range input. Okay, but now if we look at our output here, so our output for this, we actually, if we think about what we want to control, we want to control this list of points. And our list of points is actually giving us 9 values and not 8 values, like our input says. And that's because of the way that this capsule works, right? It's dividing it into strips rather than points in the thought of 8 points in one direction, or for instance, we have 5 points in one direction, but it's working with divisions of more like cutting, if you were going to cut, say, a cake in 2 strips, right? So that's going to be how we count our 4. And then it's going to be lined with a series of points that make up those strips. So what I'm saying is that for this week, we actually, if we take a look at the range output for this and for our points, these lists already align. We don't have to give it an x minus 1 because we have here 0 to 8, we have 9 values, and here we have 0 to 8, we have 9 values. So those two are working together already, and we don't need to give our steps x minus 1. We do need to take a look at what the domain is. Okay, so notice it's barely moving. Well, that's because it has a domain of 0 to 1 foot. So our list of values, take a panel here, our list of values are only moving in the z direction between 0 and 1. And we want a greater range of movement, right? Because this is 100 feet and this is 50 feet. So to move in, 0.4 feet is not really much. So to up this, we're going to give our domain end a higher number. We can give it a panel, or you can do a number slider. The number slider is a little, it can change, right? And if we remember, we don't want this number to change. We want to keep our domain always matching our graph mapper, right? The 0 to 1 and our domain 0 to now 25, they should match. So that means we have to double click on this and adjust our maxes for both our y and x direction. Okay, so now we have a much more dramatic movement in the z direction, and we can choose where that z direction is located, right? So where that peak is located for our z movement. Okay, so If we look here, we can see that output and kind of understand it a little bit better, right? So I know that my 0 point along this edge is getting, it's moving 1.5 feet or zero point 0.6 feet. The next point here, and we can see that, right? It's moving 1.6 feet. The next point is moving 4.5 feet. So this here, and 8.27 and so forth. So it's being translated from this original deformed surface into a kind of secondary surface that has a different curvature based on the changing um, changing z value. And if we want to flatten this, we can bring this down, and this will now choose a series of values, around 5 feet to say 1 foot. If we want to bring this in, right, we can create a greater height. So that's how it's working, right? It's giving this. These are giving the values of z, and that z is then being translated into our point lists. Okay. So okay, so those are our points, our shifted points. So I'm going to give it a scribble. Okay. I'm going to give it a scribble and say, this is my, I guess, remapped points, we'll call it. Okay, and then these will all be grouped together, and that's part 3 of this. Okay, so that should be familiar. We just did this last week, so I think you should be relatively confident in achieving that one. Okay, so then the last little part is to get these lofted between our bottom curves and the top curve. So we need curves, right? Right now we have just points. So interpolate, I can say that correctly. We need to take our moved points and give that an interpolate curve so that we have a curve that runs through our list of points. And if we copy and paste this and we input the other list, right, this base list of points, then we should have our lower curve, right? So I have a lower curve, an upper curve, and if I click both of them together, I can see how that works. Okay. So I have 2 very different lists of curves, and if I bring down my panel, I can see that. Okay. And now we're going to get a little bit more into that list management because we have to kind of we have to go through these and flatten and graft and kind of understand how they're speaking to each other, because it's between these 2 lists that we need to loft. Okay, so what we want to do is we want to take, and since we're starting at 0, we're probably going to want to look over here, but we're going to want to take this high curve and loft it between the high curve and the low curve, and continuing along that those lists, right? High curve to low curve, high curve to low curve. Say that 5 times fast. Okay, so that's going to be this first curve, right? So we have our high curve, so this is going to be 0. And then we want this next curve, the second curve, right? This is 1, 2. We want this first and the second item on these lists to be lofted to each other, and we want to repeat that over this surface. So if we do loft, which is what we want to do, and we take a look at what happens when we just loft these 2, what we get is we get a vertical surface between them. It's cool, but it's not quite what we want, right? These are like section cuts or something, or a spine. Not really what we want. So what we need to do is we actually need to shift this data. So if we want this first curve to loft to the second curve, what we need to do is we need to take this list and we need to shift it so that this chunk, okay, I wonder if I can use a snip. Give it a second. All the time in the world. Permanently, okay, never mind. All right, well, at least it's still recording. Oh my goodness, okay, never mind. I was going to try to sketch something, but forget that. Okay, so I have a list of 5 of these, right? What I want to do is I want to take these bottom 4 and I want them to move up, and I want the second curve to replace the top curve, and I want to move the top curve to the bottom of the list. It'd be so much easier if I had a pen. To do that, what we need to do in order to rearrange these, I'm going to simply flatten this. Okay. Notice my loft doesn't like that anymore. That's because, remember, these lists have to talk to each other. So when we do input this again, this list is going to need to match this list. Okay, but for now, we need to do some list management. So first we want to flatten it so that we have one list with a series of line items, because then we're going to bring down a shift list so that we can then take that flattened list and shift that one value. Okay, so this is actually going to work. It's going to work opposite of what I just said, in that it's going to move the 0 into the second line item, and then this is going to move to the front, which is probably also going to work. But when we look at this, so if I take this, copy paste, okay, see, it's the exact same thing. So in order to check this, we're going to graft the list so that it can match match these, and then I'm going to input that data into my lofted curves. Nothing's happening, and that's again because, remember, these have to match. Our branches, our subdivided branches aren't working, right? They're not talking to each other. They have to speak the same language. So I'm going to do simplify, right click and simplify both of these so that they both have the same path structure. Okay. And if I look over here, you can see that, okay, so something is happening. And we have to take a look then at what. Okay, so we have our first curve here. Looks like it's attaching to the second curve here. Okay, great. So that means that our list has indeed shifted so that we have our first curve here now at the end of this list. So and if we do list item, we can probably see that. Okay. Right, so our 0 index, which would be this first curve, is now at, that's this front one. It has now, and we have to go back and ungraph this, but it has now shifted this first curve to the back of the list, and this next curve has come up and become our first item on the list. Okay, and then by grafting, we are creating the same list of lists that we have above, where we're just giving them all their own path, and they're no longer in one list with 5 line items. Okay, so that's a way to check to understand what is happening. But notice I have a problem, right? Because my top curve went to the bottom of the list. Now that curve is over here, and it's trying to attach between the two. So I need to, is that what happened? Now I'm taking the last curve here. It's attaching to the, yeah, right, because this last curve over on this list, right, So this interpolated curve, this bottom curve, is trying to attach now to the last item on this list, which is now going to be that first curve, right? Since we took that and moved it to the back. So now what we need to do is we need to cull our list. We need to remove that last line item so it has nothing to attach to, right? Because we don't want this loft between these two last curves. So we can take a look at our options. Let's look at our set. So we have our tree options. We can prune the tree, so it removes a branch from the tree. But I don't think that's the cleanest way to do it. We can trim the tree. Can do different levels. Yeah, I think I'm just going to do the easiest way to do it is cull the index. Honestly, that's the easiest way. So you take the cull index, and we're going to go back and ungraft again. I know I keep going between flattened graft and a flatten and a graft, but with the flattened list, we can cull the index because there's still an index of points or of curves. If there's a graft, there's no index to cull because they're all their own separate lists. But if we have them as one singular list of five curves, then there's some sort of index to cull. And then we will always choose then just the last point by setting the integer to -1. Okay. And then we can see here what that looks like, right? So it's always going to take what was the shifted list, right? We shifted this back, so now this is the start, and then this is the end. Then we did cull index, which is we gave it a -1 as the indice. So this should be -1, which will be the last item on the list. And now I should be able to graft this list. Okay, if I look at this, I should be able to graft this list and simplify. Okay, and then input that that data into my loft. Okay, and then it should be good. Our gills should be showing. So if they're not, go through that again. I know I probably said that really awfully. Trying to explain lists without a marker board is tricky. But I think, if you take a look at Palusa's video, you take a look at this, and between the two, I would think that you'd have a better understanding of how these lists are working together. And then also remember, I always save both the Rhino and the Grasshopper file, and I place them in the Google Drive folder, the shared Google Drive folder, for you to go back and take a look at these. So I suggest always taking a look at those, and then check out the outputs from each of these. So download that Grasshopper file and then take a panel to every single one, and you should be able to compare the outputs of each and every one. Okay. Okay, so these are our lofted gills. Scribble. We're just going to say our gills. Okay. All right. So I'm going to delete the panels, but if you want, go for it and go back and add them. And then I'm also going to turn off all this previous stuff. Okay. So you'll notice that my gills are a little different, and that's because these are in color, and that's because I have my preview set here to something else. So we've gone through this before where you have no preview, draw our curves, and then draw our shading or our shape, our surfaces, right? This will turn off a preview unless you have it selected. So you need to select something, and then you can see what that geometry is. Okay, turn that off. And then this is going to be a document preview settings. So what I've done is I've changed what is a normal color to a different color. But if I select a different color, it will update eventually. It just needs a moment. But if you're tired of looking at the same red or green, if you want to change a pace, that's a way to change that. And it didn't update. I don't know why. Oh, here we go. Okay. So click OK. And now it's updated and has a new preview for you. Okay, so that's the first part where we are learning about how to make the gills themselves, and that's part of the assignment, of course. But then there's also, you can start to use these as surfaces for divisions. So we've learned how to divide other surfaces into diagrids, into waffle structures, and that's all based on a starting surface. So it took us these 4 steps to get to this new starting surface, but you can then, use your isotrim and divide domain to create a new subsurface on this. Or we can start talking about using Lunchbox. So what I have up here is, and I think I had to call this index to, if I look at the panel here before I do anything, let's check that we have what we have here. So we're getting a null. So this is coming from the fact that, remember, I had to cull the index here, and for this first part, we had, for this first curve, we actually had 5 curves, and for this, we had 4. So what it's doing is it's lofting between 0 and between 0 and 0, 1 and 1, 2, 2, 3, 3, but it doesn't have a 4th path to follow to loft between. So our 4th is getting a null value. So just to make things cleaner as we start to move forward, we want to make sure that this list is working for us, so that it's clean. So we don't want any nulls in our list. So we can call the index again, or I think we can also do, we can do test it for null validity, okay, where it will tell us what is null, or I think it's remove null. Oh, I'm getting tired and forgetting. Yeah, I don't remember right off the top of my head. Okay, never mind. Cull index, that's the simplest one. Okay, so cull index will help us again in that we can take our list, flatten it, and then we can ask it to remove that last integer. We could have also done this on the previous one, right? So we could have taken this list and done the exact same thing that we did to our shifted list before we even lofted it. But this just cleans up what the list is, right? So we have now no null items and only the surfaces that we want. Okay, so that's one part of this. The next part then is let's delete this. Okay. The next part of this is let's get familiar with Lunchbox. Okay, so if I go to Lunchbox and I go to these panels, I can start to kind of see what is available to me. So I had the generate. These are attractors and subdivisions and panel frame. Okay. Math, these are complex surfaces for me to choose from that are pre-made. But I'm able to control them parametrically, but they already have a certain mathematical formula in them, so I don't have to figure it out. Then the panels are what we want to talk about, in that if I choose, say, a diamond panel, all it really needs to create a panelized structure is a base of a surface base. So if I input my surface, right? So this is my base surfaces. Um, I need to input my base surface, and then it will automatically adjust to that surface uh, given a certain number of divisions, which is typically 10 and 10. I can up that surface division um, by just giving it a new slider, right? So I can input the U, and I can fine tune the horizontal, right? Because remember, this is axis view, so I can make that a finer division in the U axis, or I can have to input that. I can make this finer in the y-axis. As I do that, remember, it's the more divisions you do, the more work your computer has to do to try to figure it out. So as you could see, as I got finer and finer, the more time it needed to think about it. So keep that in mind as you know start to get excited about these divisions. So that's just to get the panels themselves, okay? Um, and we have other options here. We have hexagonal cells, we have quad cells. I mean, it's a lot of this are things that might take you another 5 steps to make, but this allows you to kind of cheat a little and uh, subdivide quite quickly. Okay. I notice you can see that there's a surface that is automatically made from these. So these panels are actually a series of surfaces. So you have, you can see that as I update them, that surface is being approximated between them. So I'm getting a finer, notice if I up my V divisions especially, I get a finer approximation of the surface geometry. And as I lower these, that approximation goes down, right? And I get more and more of this segmented appearance. Okay. Preview off, and then we'll see what the hexagonal cells does if I turn this on. Okay, and you can see here, kind of get a snakeskin effect. If we bring this up and input our U and our V. Okay. And so you have to kind of take a look at what these outputs are. Let's see, panels. So what we get is a number of surfaces, and from those surfaces you would have to then use them as a way of manipulation, right? So you have your deconstruct BREP that we've gone over before. What this is going to do is it's going to deconstruct that. Notice it doesn't work for the hexagonal cells. That's because what this is making for us are actually curves. So if I take my curve container, you can see that that's working. That's because our hexagonal cells are only giving us cells of a curved network, versus the panels are actually surfaces. Okay. So you have to kind of pay attention to what these outputs are, um, and then start to work with them, right? So for the diamond panels, the output is perfect diamond panels as one, and then the B output is the kind of perimeter of those panels, which uh, aren't perfect diamonds, right? They're not making the shape accurately. So so that's the panelizing. I think you can walk through that and play with them for yourself now that now you have it downloaded and you know what it is. I can't see how it would be too difficult to get good at that quite quickly. Then the other thing is the structure, right? So you're going to want to take a look at this. Notice we have grid structure, we have 2D trusses, we have diagrid. These are all things that we've already done together, and I made you do them the long, slow way. So I'm sorry, but I do think you got probably a little bit more comfortable with Grasshopper in the process. So you can see here what it's done is it's approximated the geometry again. We would need to give it UV factors in order to fine tune that. Yikes, I do not want a space rain that looks like that. But you know, it's a nice quick way to create what took us 30 minutes last time. Um, and once you get what you get is a series of lines and nodes to then further manipulate. Okay, so yeah, so these are there for you to try out and use. As one student said, I think I mentioned lunchbox, and then I said, well, they have this the truss they already have it in a capsule, and it takes 2 seconds for what took us 30 minutes, but it seemed like cheating. And he said, well, all of Grasshopper is cheating, isn't it? And it's like, well, you're right. It is kind of, isn't it? It's making the designer's work a lot simpler. Um, and the goal of this is just to get you confident and in control enough to use it for your advantage. So if you want to use this instead of the long-winded way of finding a space frame, I'd say uh, you've learned something new and go for it. I think that seems to be what I keep saying to people is go for it. So and the other thing that I think is kind of interesting capsule is this random split list. And I think that's interesting for a number of reasons, but for one, I saw a couple of students using, or they were baking their geometry and then kind of creating this eroded pattern. And this isn't going to solve that, but it is going to kind of make it a little easier to achieve in Grasshopper. Um, so you would have to play with this a little bit more, but this is a random split list. And what it's going to do is it's going to take a list and it's going to output, then we're going to need curve container for this. Okay. It's going to output a random collection of that curve network from our hexagonal cells. Okay. So for this list, we have hexagonal curves coming out of it, and that's our master list. And then there's these two other inputs. One is the seed, which is kind of the random generator. So if I just give it a different seed and we select our curve, you'll see that it's just a different kind of generation of randomness. Okay, for lack of a better description. And then you have your split. Split is going to, if I have 0.5, 0 to 5, or 0 to 1, sorry, it's going to choose where that list is split. So if I have it set to 0, it's not going to split the list at all. At 0.1, it's going to split it a little bit. 0.2 is a little more, and then 0.5, of course, is half the list is going to be split between A and B. Okay, so if I put B into my curve network, I can see that they have, is the inverse, right? So as far as pattern generation, this is kind of slightly interesting that you're able to achieve that so quickly. So that's a nice capsule to know that it exists. Okay, I think this is now usually when I take a break because I'm starting to get hoarse. But I think we can power through and get to the second part of the assignment, or second part of the exercise, which is what I talked about, that circle curvature scaling, based on the curvature of your surface. So I'm going to move this down, and we're going to take a look at that. Okay. So right. So what I did was I first divided I had to do the same thing that we did before, where I needed some sort of subdivision of my surface. I need a subdivision, and then I need to find the area of those subdivisions in order to attach circles to the center points of those subdivisions. Okay, so I really just needed an array of circles across my surface. So I had said before, right, that we could do the same thing. We could give this an isotrim and divide domain and go about it that way instead of using lunchbox. So I'm going to do that as well to get my surface division here. Okay, so I have my isotrim, I have my divide domain. Okay, and I'm going to input my surface, my base surface, into both of those, and then my segments are going to go into my domain. Okay, I'm turning off my base surface so I can see. Oh, what do we not like here? Ah, okay, so I must have had that all in the same list. I did. Okay, so there was something wrong and I needed to graph my list, and that's just because these are all in the same list, and it's trying to divide the domain with as a unit. So I need them each as a separate line item, a separate unit, so that each path is divided on its own amongst itself. Right, each of these is a separate surface. I can't divide a domain for multiple surfaces, which we learned, I think, a couple weeks ago, was that you need one surface for each of these isotrims. Okay, so what graph does is that creates a separate surface of by separating the list, right, into the separate lists. Okay, so I have my count and my domain, and I can input. I think I had a different divide domains for these as well. So it's similar to what we've done up here. So I'm just going to copy and paste from our lunchbox exercise and just input our U and our V count. Okay, and probably up that a little bit more. Ooh, not too much. So I'm going to kill my computer. Okay, it's like 12, and this can be like probably 30 something. Okay, maybe a little less so we can actually see what's happening. There we go, that's better. Okay, so so that's what I need to subdivide the surface, but then I also needed to find the area and the center point of each one of these, right? Actually, I need to find the center point, but I used the area capsule. So I'm going to take the area capsule and find the center point, and that way I can then attach a circle to each one of these items. But then if I look at that, if I look at the circle that I chose, I chose a circle with a normal, and I'm saying that because if I were to take this area centroid and I just give it a regular circle, okay, so if I have a circle that is just plane based, that plane isn't going to be it's not going to be accurate to our surface curvature. Okay, so if I look at this here, notice all of my circles are all in the same plane. So if I look in the right view, you can see that they're all going to be planar in that XY plane. So I can't actually use the typical circle that we always use. We actually have to go back and we have to use one that has what is called a normal. Okay, circle CNR is what it's called, and its inputs are the center. Okay, so the center is that area centroid, but then it has a normal, which is coming from our subsurface. So I think what I did, and if we look here, is I had to evaluate the surface to find that normal. Okay, so this has a bit of a structure to it, but I needed the points from the surface. Okay, I need the points from the original surface, and then I needed to evaluate that surface and find the UV of those points. And what the UV is the normal. Okay, so it's another way of saying kind of the point coordinate. Okay, and that gives you an output of the U and the V values, right? Like an X and a Y, but it's also giving you what is a directionality. And the directionality, if you think of it like a vector, um, it, it, it will help you. So if you think of each of these points on these surfaces, um, each of these surfaces has a perpendicular vector coming from it, and that can be found at the center point. Okay, so that's what this evaluate surface does for us, is it finds that vector and it reorients each of these what are currently planar circles to be at the same orientation as that vector that is perpendicular to the surface. Okay, so it says evaluate surface, and I need a surface closest point. Okay, surface closest point and evaluate surface. Okay, so I'm going to go back and I'm going to grab those two. Surface closest point. Okay, and I need an evaluate surface. Okay, so surface closest point and evaluate surface. And the surface I'm going to use is going to be the surface that is our base surface, right? This is the base surface from our gills. I'm going to bring that guy over. He's going to be our surface input. And then the surface we're evaluating is also going to be that surface. So we need to go back over, grab our base surface, input that as well. Okay. And then the points we're going to have is going to be the centroids. Okay. Right. I did that right. Yeah. So we need our center points that are going to go into our surface, and that's going to be what we find the normal of. Right. So if I look here, I have my area centroid, and there's a certain value to that, right? And I need this. I need the U and the V, but I also need that normal that's perpendicular. So I'm going to get the point with the point coordinates, and then I'm also going to get the UV point with the normal. Okay, so that is going to be what goes into our evaluate surface. Okay, and then that normal then should be what we can input into our circle CNR. Because this is essentially the same as the UV point data, but exploded for us to extract the normal from. Okay. If I look here, you can see how it updated, right? It updated so that it's now aligning to that base surface. And notice how each one has its own plane attached to it. So it's a good thing to understand, is that evaluate surface is going to essentially give you the output data of your surface orientation. Okay, so surface closest point, evaluate surface, circle CNR. Okay, so that's the first tricky part, is just getting these organized. Is getting this evaluated and getting the circle oriented so that it's aligning to our surface. Okay, I'm going to preview off and bring this down. Okay, I'm keeping this pretty separate so you can see where the wires are going, but I understand if you don't want to see this quite in the same way. Then the last little bit is to take these circles, and we have to scale them. And we're going to scale them uh, using a multiplier and then a curvature. Okay, so a surface curvature capsule. That's the last little bit that we have to do. So the surface curvature is going to analyze the curvature of the surface, and it's going to give us the, the, the mean values from that surface. Okay, so and then that's going to be, those values are going to be what we multiply um, the scale by. Okay, so we need to scale those circles, and then they need a certain variation of because I'm going to step backwards, right? We have to scale the circles, and then we need a variation of the scale of those circles based on the curvature of our surface. So surface curvature is here, surface curvature. Man, I think I'm getting tired. Sorry, guys. I'm losing it. Okay, so we have surface curvature. We have our circles. So we need our surface, which is way back here. Okay. And then if I take a look here, we need our UV points again. So notice we have the same UV points that we input for our evaluate surface. We need a similar we need the same data for our surface curvature, because that's going to also contain the point UV and location. So we have that, and then we need to grab a scale. Okay, so just a simple scale that has geometry, a center, and a factor. Okay, so the geometry that we're going to scale is going to be the circle. The center is obviously not going to be the center point of x and y, but it's going to be the center point of our centroid. So we're going to take our centroid and input that as our center. Notice they've all updated now so that they're scaled about those center points. And then the factor is going to be the mean. The thing is that it's so tiny, it doesn't really do much. Okay, so you can see how little it is, which is why we need multiplication in order to see that. Okay, so we're going to take our multiplication. We'll say times 5. And now we should be able to see those update. So if we up this, we can start to see kind of how the circles that have the greatest curvature, right, the greatest curvature of the surface that is being evaluated, those are getting the greatest scaling, whereas the circles that are at the least curvature, the least amount of curvature of the surface, they are getting the least amount of scaling. Maybe this is clear if we turn this off. Okay. And you can see, remember we had the surface itself has a kind of a double curvature, right? It has a extreme curve at the top, then has a slight curve coming down, right? A negative curve. So you can see that in just this point graph, really, or not point graph, the circle array, so that we can understand a little bit of what our scaling is doing. Okay, so that was using surface curvature that reads the points. We had to multiply the values of the curve variation, and then we have one last bit. We need this. We need surface split. So we have the curves, right? So we need to take these curves and we need to split our original surface. Otherwise, they're not very useful. So I'm going to do surface split. Okay. And surface split is going to take a series of curves, which is going to be what we've just created. And then we need our base surface, which is back over here. Okay. And then give it a second because it's going to need to think a little. And there we go. Okay, so then we should be able to get our fragments from which we can bake. Okay, so if I right click and I choose bake, it might again take a little bit, but we should be able to see those baked in Rhino space. Wonderful. Okay, so if I ungroup, I'm fairly certain that these guys, yeah, that each one of these is actually a continuous series of, yeah, it split them, but I need to manually grab my main surface and move them over. So I have my surface that was the circles as a separate entity from my the actual base surface that was cut. And you can see these if we turn it on to, say, Arctic or rendered or something. We should be able to see that these are now holes. Oh, I still have my custom preview on. But yes, okay, so we can see that those are in fact cut pieces. Great, okay. All right, so I am sufficiently exhausted. I'm sorry if I got a little tired at the end. It took far too long for me to make this. So I'm going to organize this a little bit better, but I will save this video and upload it to YouTube, of course, and then save the script and the Rhino file and upload those to the shared drive. Okay, I think that's it for this week. For next week, we'll be going over Weaverbird. So remember, Weaverbird was the other plugin I requested you to download. Please do that this weekend and make sure that you have access to this so that we can go through what Weaverbird can do for you. Okay, so yep, Lunchbox, Weaverbird, and a whole bunch of shark gills. That's what we've covered. Hopefully next week we'll get to do more. So on that note, I'm going to sign off and see you next week. Okay, bye.